Hi, my name is Michael Herman, and 30 years ago, while attending university, an idea had come across my mind. I had looked at what the professors were saying in my physics classes regarding energy and Einstein's equation, that the equation itself didn't match up with what was observed in the world. And I also had listened to the discussion of electromagnetic energy and the Planck-Einstein relation, and also listened to, over many years while attending high school and university, the talk that a photon acts as a particle and as a wave. And an idea had come across my mind that basically energy is energy. Whether you have an electromagnetic wave or whether you have a particle, it doesn't really matter. It's how the energy is presented. It's the form of the energy, the intensity of the energy. All of this is totally related. I went to my professor's office hours and he basically said to me, I had no business at an undergraduate level trying to resolve or unify relativity. That, obviously I had no ability the same as Einstein's or these other great men in history, that I should just forget about it. I was so discouraged, I actually left the engineering program, went into business, and for many, many years have owned my own businesses and gone on a path in the business field. But over the years I'd heard things that matched exactly what I was talking about in the professor's office hours, and I had presented some concepts that he totally rejected, and now I'm seeing the results of the Large Hadron Collider experiment in CERN that produced the Higgs boson. I've heard the string theory come out in the meantime, and it basically all aligns with my thoughts that I had all the way back then. And so I'm going to make a YouTube video. I actually created an equation in June of this year based on the ideas and the thought processes that I had. Excuse if I'm not using the exact symbols, because I don't have the formal physics education, because I walked away from that 30 years ago being discouraged instead of encouraged by my professor. And so the concept is what's important here, not the actual, whether I'm writing a symbol or the equation exactly correctly with the symbols. The equation is correct, the symbols may be wrong. What I believe is the universe is extremely simple. There are just a few ingredients. I'm a firm believer in Occam's razor. The conclusion with the smallest number of assumptions is most likely the correct one. I do believe in the conservation of energy. Energy is neither created nor destroyed, only transformed. And the conservation of momentum. An object at rest or in motion will stay that way unless acted upon by a different force. Now, I believe the universe, prior to the Big Bang, or even if it's a transitional thing, the Big Bang becomes the Big Crunch, becomes the Big Bang. What basically you have, without getting into super details right now, we can go into other videos later. You have extremely basic ingredients. Everything that's complicated in our world is interactions of the forces and the things that are created out of the basic ingredients, sometimes reacting back on themselves, sometimes reacting with other secondary and tertiary forces. But the primary ingredients of the universe are extremely simple. We don't need to create extra dimensions. We don't need to create multiverses. Everything that we have can be explained with what we know about the world, about the universe, about everything. Where Einstein ran into some difficulties was his math was correct, but he oversimplified. The mathematics that he was using caused his own confusion. And unfortunately for him, he was brilliant enough to figure it out. It's sometimes people paint themselves into a corner and they can't get out of it because their thought process puts them in that direction. You have to think outside the box. The ingredients that I basically am going to say here, and I'm adding the word strings to the Higgs field because I'll explain in a minute what ends up happening. But basically, you have three basic ingredients. You have the Higgs field, which is the force in the universe. It's the primary force of everything. You have your electromagnetic forces, you have your nuclear forces, you have gravity. That all is a secondary force or a tertiary force. Energy. Energy is what creates everything. And then you have your natural quantum vibration, the speed of light. That is a restricting factor. That is like a constant that everything basically falls to. Anyway, so based on that, based on saying let's build our universe from the simplest up instead of looking at the complicated and trying to look back down, and then testing this hypothesis to see if everything works, which will be in other videos as well. I basically, when I went into my professor's office hours, I basically put up two equations, or I put it in my notebook at the time, and I put, okay, now both of these equations are missing something. Einstein himself knew it. He observed that energy is created when mass is accelerated to the speed of light, but the mathematics says c squared. Well, c squared is important. It's critical because we measure gravity as meters per second per second. So we have to have the c squared. And so mathematically we can't eliminate that. Now a lot of people nowadays are saying, oh, we want to say E equals mc, or we will say E equals m. Okay, a lot of professors are now teaching E equals m. Okay, yes, mass is created. It wouldn't exist without energy. But that's an oversimplification. That's, you know, we're looking in the wrong direction. We want to, if we want to merge gravity, we want to create a unified equation, you can't eliminate the math. You can't oversimplify. This is correct. Einstein had it correct. But it's the problem comes, it's overly simplified. Unfortunately, we have to drag this equation out and find where that error happened. This equation is observationally correct, but it's leaving something out too. So this equation, in my mind, violates the law of the conservation of energy, and we'll get into that in a moment too. So, but they are both observational equations. So if we look at an electromagnetic wave, a photon, behaving as a particle and as a wave, we need to say, hey, a particle, if it's a particle, it behaves like a particle, but also can act as a wave. Now, we don't observe the wave. They're beginning to now, when you say, a lot of physicists are saying they believe that matter is a vibrating string. Well, you know what? In saying that, they're onto something that I was onto 30 years ago. Now, at the time when I was at the physics professor's office hours, I didn't call them strings. I basically said a particle was a segment or a box. But I like to call it a segment because I believe the universe is Cartesian. The universe basically, before the Big Bang or before the addition of energy, is a two-dimensional thing. The Higgs field lines are there before the Big Bang. You've got this giant Higgs field, and the lines themselves, any line is two-dimensional. It's 2 points, and it's a two-dimensional connection in between. Now, what happens? We want to look at the universe, so let's take this down. We look at the universe, so we have the Big Bang, we have a point, and we have an explosion, and you have, we have all these lines. Now, one of the things that caused me to be here today was when I heard the result of the Higgs boson experiment. They said that the universe acts as a jelly. This was something I said to the professor in the office hours many years ago. I said, I didn't call it a jelly. I called the universe, basically, with the addition of the energy, a non-Newtonian fluid. There's empty space. There's, where there's no matter or there's no energy. But that doesn't mean something doesn't exist there. You have the Higgs fields lines all radiating out from what was the start point of the Big Bang. When the Big Bang occurred, you had all of this energy. It couldn't get out of its own way. It was so intensive that, you know, it accelerated outward from the singularity that was the middle point of the Big Bang. And that energy crushed on itself. It couldn't get out of its own way. And that's where they're saying the Higgs boson was created with a massive amount of energy, but it disintegrated very quickly too, because it's a particle that's just too big to naturally exist. We created it, but it had such a short lifespan because now we are in a deflated state of being from the Big Bang that no super large particles can exist naturally without containment. This is one of the things, and we'll get into this in future videos, but I don't believe micro black holes can exist because it would be too much energy in too small of a point. Just like the Higgs boson particle could only exist for a second, we can create atoms, supernuclear atoms that have a lot of nuclear mass. They don't exist very long. Everything basically, we can create fusion by putting more energy in than we get out. But again, on a small scale that isn't the core of a sun, it can't sustain itself. So the same thing with a particle. You can't put too much energy in too small of a box or it ruptures and creates smaller particles. That's just the natural order of things. And that's what I basically said, is that the field lines got crammed with energy and they shattered. So basically what strings are field lines of the original universal field, the Higgs field, with energy just cramming out so fast. Now, energy, obviously, it's not when this explosion happened, it wasn't clean, it was messy. It was very messy. You had electromagnetic waves created, so you had energies of all different sorts. Particles were created, electromagnetic waves were created, light, X-rays, all of that. But it's all energy just trying to get out from the center. So let's take a look though. What is the difference between a particle and the energy wave? Well, the particle basically is energy over a segment. We're going to call it strings now. I'm going to accept the word string. I called it segments 30 years ago, but it's basically a string. Now, there's energy. What contains that energy? Well, the energy, this is a two-dimensional thing. When we put energy into it, we are actually creating a third dimension. The string is two-dimensional. The energy is a wave on that string, a vibration. And if you look at it now, you now have a third dimension. I'm going to use this balloon as an example. That would be your string, and this would be the wave. Now, it's a very important concept, and this is very important for gravity as well. What you have, if you have this string, what is containing the energy? Well, there are two things containing it. And it's very interesting because there's a pairing here. You have two things containing it, and there are two components to gravity. The first thing containing it is the actual force of the Higgs field itself. The energy is pulling away from this segment of the field line. And the Higgs field is, the force of the Higgs field is pulling back. So it's creating that wave. So what happens is it accelerates back, and then it bypasses, and it comes back, and it bypasses, comes back. The secondary thing is, depending on the angle, see, electromagnetic waves, light waves or whatever, have very low energy. So what you have is a wave that looks like this. And the energy in a particle, the wave would look more like this. Very, very, very steep. Why is this critical? Well, what I'm postulating with this force of the Higgs field that is pulling into the original string, what you have is, if the angle is really, really steep, the energy, when it hits the end of this the end of the certain length of the segment before it reflects back on itself, it's coming in at such a steep angle that it glazes off the end of the particle. It does not pass through the end of the particle, and it comes back. And it does this pretty much until another force acts upon itself, forever. Or possibly the string can fracture if there's too much energy. And how can that happen? Well, you know, strings can absorb other waves, create interference patterns. You know, you can add energy to a particle. Obviously, your skin warms up when you're in the sun, so energy can be added. But remember, the energy that we add, compared to the energy that's contained within the string, is very, very minor. So we have to come up with creative ways to add more energy to a particle to get it to a breaking point. But anyway, so now if we accept that this energy is bouncing back around, well, this presents some interesting ideas. If we look at this particle now, well, if this energy is bouncing back and forth in here, we have a natural quantum vibration, the speed of light. So you have a wave within this box that is actually traveling at the speed of light. So this is constant. You have a c here. Now, if this is a particle, okay, now you've got an equation for a particle that you can create. And if you want to say what is the energy, how do you release the energy out of the particle? You have this particle, you accelerate it to c. This was the oversimplification of the math that Einstein's equation, E equals mc squared. You can't say c squared because these are two different c's. If he were to write the equation and look at it always as mc1, c2, he would have been able to say, okay, let's forget about c now. We're not going to call it m because I'm creating confusion. By calling it m, it really is particle c cubed, and that's wrong. So we don't want to do that. We're going to now call this a particle. And there's the simplification of looking at it, but we want to actually describe now the energy, because different particles of different sizes have different energies. And we're going to also look now at the interactions and how this energy, when we accelerate it, is released, or how energy in an electromagnetic wave can be captured into a particle, because that's another interesting concept as well. Because one of the theories that when I was thinking about and creating this equation that I came up with is neutrinos, being very, very small, low energy particles, actually are electromagnetic waves that are actually recaptured and crammed into a little box and become particles. And so, like for example, at the event horizon of a black hole, that's basically a super accelerator which creates black holes. So we're saying, hey, black hole is absorbing light, but I would say at the event horizon, at least, if light goes directly into the black hole, yes, it is absorbing it, but at the event horizon, if the light is glazing by the black hole, it actually could become a particle, a neutrino, and we don't see the neutrino, so therefore we don't see the light. So the energy, again, it's transformed. It is not destroyed, it's not whatever, it's transformed. And being absorbed can be a transformation as well. So again, I always believed in the conservation of energy, but let's get rid of these waves right now. Now we have this particle. We want to describe the particle itself. Well, how do you describe the particle? What is this particle? Well, we don't know. We can't see this little segment. So how do we describe it in a way that will work no matter what? I would say we have to describe the length that this wave travels along. So what you're going to do, I'm going to use m for this because the m actually is correct if we get rid of the c squared. M is going to be a length, a certain length of whatever this string is. And that length is going to be defined as the Planck length. There's a smallest possible length that can exist. Now, calculus tells us you can always divide something in half and a half and a half again, but we observe that the Planck length is the smallest length. My contention is the smallest length is observable length is the smallest possible particle you can have. So if we're going to say we're going to use some variable of the Planck length, we're going to have to say then that x, the length of this particle, has to be greater than or equal to 1, because we're multiplying by the Planck length, and the Planck length is the smallest length. Now, what we're going to do then is we're going to look at this wave. Well, what are the two key factors of this wave? Well, one which that this equation leaves out, and that's why I say it violates the conservation of energy. One of them is going to be the wavelength, which comes out of the frequency. So wavelength is important. But there is something more important that Max Planck missed and Einstein missed by the simplification of the math: amplitude. Amplitude is critical. Now, why do I say amplitude is critical? Well, if you look at a wave in an ocean, the higher the wave, the more the energy. It only makes sense. Same thing all the way down in a particle. The higher the amplitude. So if you have one particle, let's call this one particle, and it's a certain size. If you're going to have a more massive particle, it could be either more length with the wave traveling along it, or it can just be more energy. And this is how you can, with electromagnetic waves, a microwave oven heats up your food. You can actually add energy within the particle itself, and you create a more massive particle. Now, we want to unify gravity as well. And that only makes sense if you put more energy in there, you've got more force of the Higgs field containing it. So you've got more, the energy is fighting the Higgs field. And so what ends up happening is the particle becomes more massive because you've got more energy in it. The mass is directly related to the energy. So now, if we say that the Higgs field is critical, a critical component of the particle, it is fighting against, and again, you know, I'm just drawing up with my limited knowledge of physics, so the equations may be, you know, the symbols I'm using may be wrong, but I'm going to call this the force of the Higgs field. Okay? So, now you have a particle. M is equal to the variable length of the Planck length times the wavelength times the amplitude over the force of the Higgs field, because that is basically what contains the energy. The Higgs field is pulling. The energy wants to fly off, just like a person standing on the planet. The gravity is holding us down. If the gravity wasn't there, we'd fly off into space. Well, it's the same thing. The energy wants to fly off. It wants to go away, but that original field in the universe is holding that energy in, containing it in that particle. So, anyway, there you have it. So now you have, and I'm going to rewrite it above. So now we have an equation for mass. Over. Now, again, where x is greater than or equal to 1. Now, like I told you, and I'm going to write this underneath, even though we don't see a C here, this is C, okay? Because the wave within the particle is traveling at the speed of light. That is constant. That will never change. The only variable, and again, maybe if Einstein had written E equals m variable C and then the secondary C, or variable c, because this is a constant c. If he had written it this way and he had realized that no matter what, one of the c's is always there, then the secondary c, and this is where, you know, he notices time coming out. As you accelerate the particle, you know, things are happening. What's happening is the wavelength is getting crushed down, and we'll go over that in a minute too. When you accelerate a particle, when it hits this c, the energy comes out, but you already have the c in there, so the E equals mc squared, mcc works. Okay? So if then you want to say, okay, now we're going to look at what is energy. Energy, then, we're going to take this out because this, we're going to keep the particle up here. Energy is X LP and A. Okay, and we're going to add, let's see, there is your equation for energy. Now, something very, very important. Obviously, this is, I'm looking at the energy on a quantum level and the mass on a quantum level, but if you want to bring this out to the macroscopic level, you're just adding, it's basically the sum. The sum. All right, now, gravity. We want to unify gravity into this. Well, we've got this picture of a particle. I'm going to write it in red. What is gravity? Well, gravity is defined as force over mass. Now, there are two components here. If we look at the particle, we understand the particle. I actually see two components of gravity coming out of this. One of the components of gravity is going to be obviously the force of the Higgs field pulling the wave back down to the segment of the Higgs field. And the secondary component, well, you're changing direction. So you're changing a vector. Because when it hits the end of the particle and it bounces back, it's contained in the particle. When it bounces back, you've now got to change a direction. So let's write this out. Gravity equals, okay, so if we've got a force, again, primary force, it's the force of the Higgs field, because the particle, the energy wants to come back to it, over mass, which we now have an equation for mass, X L P lambda A over. But that describes the force that's pulling back to the field line. So we have to add the change of vector. So we have delta x, change in direction, or I'm going to say delta d actually, I'm sorry. Delta d. And what do you have? The change in direction of the energy in the particle. So, there you have an equation for gravity. This is one of the reasons why there's a particle, a wave, electromagnetic wave, a photon, can have characteristics of a particle. As it's traveling along, any particular snapshot, this is the calculus, any particular snapshot of that particle at that particular instant in time actually behaves, that wave behaves like a particle. But the thing is, there is no containment point for that light because the angle is so low. I mean, if you're looking at light traveling through a particle, it's coming in at an angle that it wants to escape. Now, the perfect example is, let's look at the end of a particle, and we'll call it like this screen. If you come in at a very, very, very slight angle, it'll pass right through. But if you come in at a very steep angle, it will glaze off of the screen. I mean, it's just an example. It's obviously not how the particle itself works. We can't actually see how it works, but we can observe that glazing off, that energy being contained in there, has to happen along those lines. So the light is traveling where it's not really quite enough energy to glance back off and rebound within the particle. It passes through. It passes through all of the strings in the universe. But at any particular instant, the snapshot, it's got energy. That's why it has a tiny amount of gravity, so it can be absorbed by a black hole, or pulled in by a black hole, I should say, because in some cases it's not absorbed. It actually hits the event horizon and gets accelerated. But no matter what, the electromagnetic spectrum has very, very small energy, which is one of the reasons why Planck, when he created the Einstein-Planck relationship, he left out amplitude because it really wasn't observable. But amplitude is critical no matter what. Just because you don't observe it doesn't mean it isn't a factor. And the reason that I say amplitude is critical is, according to the equation without the amplitude, if you have, say, two cities, and you have two roads, we're going to say one road is this, and another road is this. Planck and Einstein focused solely on the frequency. So both of these have the same frequency, because the frequency is the distance of the wavelength times the speed. So if the frequency is the same, but the roads are of different lengths, I would challenge anybody to tell me to drive one road and use the same amount of gasoline driving another. Or another way to say it is, let's just say this wave, this length right here, represents a flat wave. So we have a wave like this. Okay, that is always going to be the same energy. In order, you can have the same frequency with a longer length. But that longer length, when in the form of a wave, represents more energy. So it's a violation of the conservation of energy not to have a component of the wavelength in that equation. I really don't care about that. That's, you know, again, when you unify and you come up with an equation, and you have the wavelength and you have the amplitude, you've covered the energy. Now, according to this equation, and it makes sense, time is irrelevant to a particle. It's reflecting back within itself, so it's timeless. And see, Einstein, all of his work was related to time. So now, when we're looking at all of these equations, we now understand the universe was Cartesian or two-dimensional before the introduction of energy. Energy added a third dimension, and if you look at the quantum vibration, what you've now got is time, which is what we recognize as the fourth dimension, is a derivative. Time comes out of a rate, the speed of light, but that speed of light is built into the natural quantum vibration. So we now have equations that basically explain everything: mass, energy, gravity, and again, we've now unified all of them. I may not have actually drawn the right symbols or whatever. I basically look at a particle and I see it. This is my best way of describing it. This is what happened when I went to the office hours and I was writing things down, and the professor, oh, you don't use that symbol, you don't, and I was trying to get the concept across that basically, it's the concept. I hope I described this well enough, but it's the concept of what this particle is. I see the particle, I'm picturing it, I'm just trying to put it into symbols so that the world can understand it. That's all I'm doing here. And I think this is a good start. I will have other videos where I describe other things like what we observe in the universe. We basically say dark matter exists. Well, I don't believe dark matter can exist, if it's supermassive, that is, because basically I don't believe the particle can contain it. And I'll draw some diagrams and stuff like that in those other videos to show. Redshift makes sense to me, and I'll describe that too. But one of the things I want to describe right now before we get on to that, just as a teaser for the next thing, if you accelerate a wave at the speed of light, or to the speed of light, what you're basically doing is, and this is one of the reasons why the Planck length is so important, if you accelerate the particle, and this is what Einstein had noticed, the wavelength, the wavelength gets compressed. So we observe, as an outside observer, the light going away from us red shifts. But within the particle itself, it blue shifts. So what we have is, as we accelerate it, the length gets squeezed and the amplitude gets bigger. Conservation of energy. The energy is transformed. Now, I believe at the speed of light, or maybe even below the speed of light, depending on how much energy is in the particle, because that could be a factor as well. Say this is your particle, and the air inside of this little bag is the energy. Well, as you accelerate, the particle is getting smaller, and the force of the energy inside of it gets big. When you hit the speed of light, basically what ends up happening is the energy contained within the particle explodes out of it. So that's what's happening when you accelerate the particle. And this equation right here actually jives with that. So here you have it. I'm introducing this to the world. I tried since June to get professors to listen to me. Nobody returns any phone calls. Nobody returns any emails. So I'm putting this out on social media because basically what's ending up happening is a lot of people have a lot of ideas, and these equations will refute a lot of the ideas that are out there. I hope you enjoyed this video. I'm sorry if it was so long. Have a good day.